Today we're going to be talking about practical SMT solving, and I want to emphasize the word practical because when I was doing my research for this presentation, a lot of the white papers and videos and articles I came across were like extremely academic, and so there's like this big distinction between, or this big rift between what's studied in academia versus what's used in the industry, right? So a lot of what's studied in academia is really theoretical, and a lot of the research is aimed more towards creating prototypes rather than what people use in the industry. And so my goal for this talk is to introduce SMT in a way that strays away from like the theory and the math that's behind it, and to focus more on just like what SMT solving, what an SMT solver is, and just how to use them. So hopefully by the end of this talk, this comic, which probably doesn't make any sense to you guys right now, will make sense by the end.
Yeah, are you recording?
Yes, we are. Why?
Just wondering.
Oh, okay. So what is SMT? So according to Wikipedia, I just realized this dimensions. Totally. Okay, anyways.
Aspect ratio is off.
Whatever. Anyways, so according to Wikipedia, an SMT problem is a decision problem for logical formulas with respect to combinations of background theories expressed in classical first-order logic with equality. So that's like a big earful, right? You can probably... Let's just forget about this for now, and let's take things like step by step. And let's first talk about what first-order logic is. So you guys maybe have learned this in your CS classes. Maybe not. But in case you haven't, first-order logic is an expressive formal language system that breaks statements down into things, relationships, connectives, and quantifiers. So for things, you have stuff like constants, so you could have like x and y. You can also have functions, so foo of x, bar of y, and you can also have relationships, so predicates. So predicates are basically functions that return true or false, and an example of a predicate would be an assertion. So an assertion is basically a predicate that's inserted into a program that's assumed to be true. And so at runtime, if it evaluates the false, then you get what's called an assertion violation. And when you get an assertion violation, that causes execution to abort. So you might be wondering, like, what's the point of having an assertion? So using assertions is pretty common when you're debugging, just to make, just to force the program to fail more obviously if the expected assertion condition is not met. So then you have quantifiers like and, or, not, and then quantifiers. So you have for all and there exists. So that's what first order logic is. So knowing what we know now about first order logic, let's revisit the definition of what an SMT problem is. So this is my really crude definition, but hopefully it's more clear or it's easier to understand than Wikipedia's. So basically an SMT problem is a decision problem or a question that returns true or false for formulas expressed using first order logic that return true or false based on theories of arithmetic, lists, bit vectors, arrays, etc. If this still doesn't make any sense, that's okay. I think it'll become more clear once we talk about how SMT solvers work. But hopefully this gives you guys like a general idea of what an SMT problem is. So what is an SMT solver? Essentially, so knowing what an SMT problem is, an SMT solver is basically what it sounds like. It's a tool that is used to solve SMT problems. So it's basically a constraint solver. And in this context, a constraint is a statement that specifies properties of a solution to be found. So to give an example, can I get that whiteboard, please? Actually, is there even a pen? Oh, do you even have a pen?
I thought there would be one here.
Yeah, I thought we had pens in here. No, it's fine.
Yeah, let's get a permanent marker.
It's been up for like a whole semester.
Probably
It's
know
like
that.
once
Every
ago.
ship is a minesweeper once.
Huh?
Yeah, but only once.
This isn't like a permanent one.
No.
That's in the corner first.
Oh, great.
Oh, purple. Purple.
So you have like, for example, x is less than 3. X is greater than 1. What is x? So the constraints would be, so number of constraints is stated that specifies properties of the solution to be found. So the solution to be found is what?
2.
Yeah. So these are the constraints basically. There's something right. Easy. Okay. It's like first grade math. So, okay. It's simple, right? So these are some examples of SMT solvers. And I not only put a star next to Z3 because it's supposedly the best SMT solver that currently exists,
What is?
Z3, but it's also the only one I've actually used. So today we're going to be using Z3. So now let's talk about how SMT solvers work. So basically, there's a few steps. The user specifies the formula that must be satisfied. In other words, the constraints that must be satisfied. And then the solver, the SMT solver, attempts to find the solution that satisfies the formula. And if a solver can find the solution, the formula is said to be satisfiable. If a solver cannot find the solution, then the formula is said to be unsatisfiable. So now let's talk about how we actually generate constraints from a program. So we generate constraints using a technique called symbolic execution. So symbolic execution is a program analysis technique that treats input data as symbolic variables rather than concrete values. So if we look at the code on the right, the pseudocode, so basically what this code does is it's reading a value from standard in, and then it's x is equal to that value, right? So basically, if you're looking at this from a symbolic execution perspective, what you would be doing is instead of reading in a concrete value, you would assign the symbol s or y or whatever to x, and so then it would follow the next line, x is equal to s times 2, and then the third line you would substitute x with s times 2 is equal to 10, right? Rather than taking a concrete value and putting it in. So that's what symbolic execution is. It's creating expressions or constraints based on symbolic variables. And symbolic execution is used in conjunction with a constraint solver like Z3 to generate new inputs or test cases. And together, this process is called concolic execution. So here's a visual interpretation of what symbolic execution looks like. So you can see the code on the left, and then the corresponding binary tree on the right. So at the root you have like alpha, right, of the tree, and then based on whether or not that condition, so this corresponds to this, right? And then if it's true, then you go here, right? So if it's false, you go here, and you read the next constraint, which is beta less than 5. that's true, then you do it. Not A, then gamma. Right? Or you go to this extreme, not A, gamma. If it's false, then you don't do anything inside here. You get this. So you can follow this whole tree down. And there's basically 5 path conditions, right, that are possible in this code snippet. So hopefully this makes it more clear like what symbolic execution is. So now let's talk about how SMT solvers are used in the context of software security. So you can use concolic execution for software verification. So basically, you use these. So you take these constraints, right, that are generated from symbolic execution, and then you feed them to a constraint solver like Z3, and that together, the process is called concolic testing or concolic execution, and that can be used to aid in fuzzing or software verification, and the raison d'etre is to maximize code coverage, or the reason we do concolic execution, the main purpose is to maximize code coverage, to follow all the code paths that exist in the program. So why do we want to maximize the code coverage? Well, when we're fuzzing, like the more code that we're able to cover, theoretically, the more bugs we're supposed to be able to discover, right? To follow more code paths. Okay. So again, concolic execution performs symbolic execution dynamically while the program is executed on some concrete input values. Yes, you have a question?
What's fuzzing?
We will get, yeah, so we'll cover that in the next slide or next slide. Don't worry. Yeah. Huh?
Brute forcing-ish.
Kind of.
Smart.
We'll talk about it.
Yeah.
Patient guys. All right, so yeah, this is just another example of concolic execution. So when you do concolic execution, you're running the program multiple times, and each time you run it, you solve another constraint in order to generate the next input value. So in this example, there are, okay, so in the middle, but basically this is a constraint tree. You probably can't read this because of the constraints. And then, so yeah, there's 4 possible paths, right? If you look at this code. And so you'd have to run this program 4 times in order to cover all the possible code paths. So what's the problem with this? Yeah, it's slow, right? Because you have to run it 4 times, right? Even so, theoretically, you're able to cover all the code, but it's just a little slow. That's the disadvantage of concolic testing.
So why can't you write a script to run in each one? So
What do you mean?
if you have each, so you have 4 different states you need to run, right?
Yeah.
So what, if you have like a list of each state, why is that in a file where you just run the script to run it all?
In order to traverse down the call graph, you need to solve each one individually.
Oh, okay.
You can't do it simultaneously.
So they're completely different, it's not the same algorithm for each one.
Yeah. No, it is the same. Well, in this case, it's the same algorithm for each one because it's just like, actually no, it's not the same because it's comparing it to A. The first one compares it to A, the second one compares it to B, the third one compares it to C, right?
I can't read it, so.
All right, so fuzzing, you were just asking about it. So I'm probably going to get reamed out for this later when I upload this on the internet. But so here's a really crude definition of what fuzzing is. It's basically when you feed the program like random input and you try to make it crash using the random input, and based on where it crashes, you're able to ascertain certain information that can aid in the process of exploit development for example, if you need to find the offset of the return address, you can. Yeah, I guess that doesn't make any sense, but
Drilling around in the dark.
huh?
Drilling around in the dark.
Yeah,
Go
that's
for
a
it.
very really crude definition because fuzzing has like evolved over the years, and so it's not just it's just like automated testing, I guess, of programs. Just okay, for simplicity, let's just say it's when you feed a program an input. That's all it is, and you want to make it crash. That's the idea. Okay, so there's two types of fuzzing. There's black box fuzzing and there's white box fuzzing. And so black box is when you don't have access to the source code. So, and then the input is randomly generated. So an example of a black box fuzzer would be Peach, which is what you see on the right. So you see that. But it's Peach fuzzer would be an example of like a black box fuzzer. And then a white box. So white box fuzzing is when you do have access to the source code, and so because you have access to the source code, you're able to reason about the structure of the code, and you're able to generate test cases or input intelligently. So like we were talking about, concolic execution, example of white box fuzzing. Can you see it?
Kind of.
Like,
Not read from that.
are you actually trying? That's the code in the Peach fuzzer is not
No,
important.
no. I can see that just fine. I'm looking at this.
Okay. You can't.
Why can't you fix
I
it?
don't have my glasses on
I don't know, but we're already recording, so I don't want to waste more time.
Okay. No.
Okay, so black box fuzzing limitations. So what are the chances? Okay, so if we look at the code on the right, let's say we're trying to fuzz this program, and so basically X is user input. It's read from user input. And so if we're using black box fuzzing technique, it's just like we're randomly generating input, right? So let's say we want to test this program and call bar. In order to call bar, there's only like one possibility, one solution, right, for why that can exist. But if we're using black box fuzzing technique, you know, what are our chances of actually randomly using that input? Right? It's not very high, right? If we're on a 32-bit system, then it's 1 to 32. If we're only using integers, right? So obviously this is not a smart technique. That's why they call these dumb fuzzers. So it's slow and it doesn't scale well. So that's one disadvantage of using black box fuzzing technique. So in contrast, white box fuzzing generates input intelligently, like we mentioned before. None of this should be new. I think we already talked about all this. So it's just concolic execution. So Sage is an example of a concolic execution tool. And it was developed by Microsoft. And it's actually exclusive to Microsoft Research Center. So it's not open source and it's not publicly available. But basically it's a framework. So there's multiple steps to Sage, right? So first step is to run the program with the first inputs. And then you gather constraints on those inputs at all the conditional statements or all the predicates. And then you use a constraint solver to generate new test inputs. And then you run the program again with the newly generated test input that should take you down the new code path. So that's basically how Sage works. So Sage, supposedly, according to Microsoft, it cleaned out a third of the bugs in Windows 7 before the operating system was actually released. And so, have you guys heard of the ANI animated cursor bug? So basically in 2006, there was this ANI format animated cursor bug that was found by this guy named Alex Soderov. And so according to Microsoft, black box fuzzing techniques of the code failed to uncover the bug, but their white box fuzzing technique using Sage was able to uncover the bug within a few hours. So supposedly it's able to find some bugs that traditional, more established fuzzing techniques aren't able to find. So in theory, it's supposed to find 100% of the bugs, but as it turns out, that's not exactly the case, as we'll talk about in a few slides. But if you guys read the bottom,
Yeah.
so the last row is a combination of white box and smart fuzzing, right? So obviously, like we mentioned, that takes the longest because you have to run the program multiple times, but it's supposed to cover 99% of the code, right? And then 100% of the defects. But this is in theory. That turns out it's not really the case. But we'll talk about that in a few slides. All right, so now we can talk about Z3. So Z3 is an SMT solver. It's open source, I believe. And basically the way you use it is so remember with SMT solvers, they take in constraints. So you're able to add constraints by adding assertions using Polish notation. So you guys know Polish notation? You should know. I had an assignment on this. Like, what does that say? What does the assertion say? It's just A is greater than 10, right?
Oh, you mean
So you put the operator. Yeah, Polish notation is the same thing as prefix. They're the same thing.
Oh, okay.
Yeah. So Polish notation, prefix notation, same thing. So the operator goes first, right? Okay, so pretty simple. And then, so you add the constraints, and then after you add the constraints, you check the satisfiability using checksat, and then after that, you get the interpretation that makes all the formula true using get model. So, okay, here's an example. So this is an example of a formula that's unsatisfiable. So you shouldn't be able to solve this, right? You shouldn't be able to there shouldn't be any values that exist for x and y that make this formula true. So we can test this out. You can read that it says unsat at the top. So make it bigger. It's gonna look bad on the recording, but okay.
No, you can't. That's fine.
Okay. I mean, okay, just trust me. It says unsat at the top. So if we change this to make this satisfiable, then it says sat. So it's satisfiable, and then ignore the part at the beginning. So the solution is 1 and 2. So x is equal to 1 and then y is equal to 2. So all we did was change this to this. So this is a satisfiable formula. Does that make sense? And does the code make sense? Like, so first we're declaring the constants, and then we're adding the constraints, and then we're checking if it's satisfiable or not, and then we get the model. Okay. If you don't like prefix notation or Polish notation, no, there's good news. So we can use Python bindings. So this is the same thing as before, only in Python. So let's see what that does.
So Python can really import anything.
Yeah, pretty much.
I guess.
So yeah, it says it's unsatisfiable, right? But again, if we change it, oops. We get the solution: x is equal to 1, y is equal to 2. So I prefer using the Python bindings. I don't really like adding constraints in Polish notation. But yeah, I think this is a lot easier to read also. So this code makes sense. So yeah, you can use this to do stuff like solving Sudoku. You guys all know how to play Sudoku?
Yeah.
Alright, so basically, in case you haven't, or in case you don't know how to play Sudoku, the rule is, the objective is to have the numbers 1 through 9. So you're given a 9 by 9 square, right? And then within each cell of this 9 by 9 square, what? Oh, thank you.
Use a pointer.
Yeah, so whatever. Okay, so each column needs to have the numbers from 1 through 9, and each row also has to have the numbers 1 through 9. And each of these 3 by 3 squares that you see, they also have to have the numbers 1 through 9. And then typically, when you're given a Sudoku puzzle to solve, it'll have some of the numbers filled in already, such as this one, but not all the numbers. And then the objective is to fill out the rest of the 9 by 9 square. So you can use an SMT solver like Z3 to do this. I didn't have enough time to come up with my own proof of concept. So I found the solution online. Not this. This. So someone used Z3 to write a Sudoku solver. So if you look at that, it's basically like a ASCII text version of what you would be given as a Sudoku puzzle to solve, right? It's a 9 by 9 square. It's not really a square here because it's in the shell, but you guys can see how that's a Sudoku puzzle, right? Yeah, okay, cool. So then to solve this, yeah, you can use Z3 to solve this, and this should give you a fully solved Sudoku solution based on your input. So yeah, basically it's taking like linear equations and solving them, and then coming up with a solution based on the solutions. Okay, so that makes sense to everyone? Okay, so last thing we need to talk about is why this isn't a perfect technique. So as it turns out, even though in theory concolic testing is supposed to uncover 100% of the vulnerabilities in the program, the majority of remote code execution vulns found in the past several years were still attributed to using dumb fuzzing techniques. So you might wonder why that is. Well, a lot of it has to do with the fact that Z3 is open source, but a lot of concolic testing frameworks like Mayhem and Sage are closed source. So have you guys all heard of the term security through obscurity? Yeah. So
Security to security.
obscurity.
Yeah.
Yeah. So Do you guys know why that's a bad thing? Somebody
No
want
peer
to
review.
volunteer? Huh?
No peer review.
Basically, like the idea is the more eyes you have on like an encryption algorithm or just like a program that's supposed to be secure, um, the better chances there are of uncovering bugs or whatever and fixing those bugs, right? If you have more people looking at it. So that ties in with Kirchhoff's principle, which applies to like encryption algorithms. So yeah, this Sage and Mayhem, they're closed source, which is weird because that's not typical for in the security community. So yeah, it's difficult. It's difficult because it's closed source to find flaws in these frameworks and to improve these tools. And there's one study that said Mayhem, even though so Mayhem is this concurrent testing framework that was developed by Carnegie Mellon. And so even though it was able to identify thousands of bugs in this one application, most of them were extremely trivial. But again, we don't know like what the problem is with that, right? If it's closed source. So another thing is like a lot of comparisons between concurrent testing frameworks and more traditional vulnerability discovery techniques are done in retrospect, right? They're done in retrospect, right? So this is bad because if you're performing analysis in this manner, it leaves you susceptible to like to cognitive bias, right? Does that make sense? Do you have a question?
Sorry, can you repeat that?
Oh, so okay, so basically, a lot of comparisons between concurrent testing frameworks like Sage and traditional, more established fuzzing techniques like Peach, for example, Dumb Fuzzer. A lot of the times when they make these comparisons, it's for bugs that have already been established or that have already been found. Remember how we were talking about the ANI bug? Like the ANI bug was already found, and then they decided to compare if Sage would find it versus if the Dumb Fuzzer would find it, right? But that's not really a fair comparison because if you know which code path will trigger the bug, then that leaves you the cognitive bias, right? And then, so that makes sense?
Yeah.
Okay, cool. So yeah, this technique isn't perfect, but I'm sure like as research continues, and hopefully they make this open source eventually. Who knows? But this is a relatively novel technique that's still in its infancy. So Sage hasn't been around for that many years, relatively. So yeah, concurrent testing is still in its infancy. So I'm sure like as time goes on, we're going to see more and more improvements in this technique. But supposedly this is the future of like automated software security testing.